Also, I'd like to thank everyone for being here tonight and for Rackspace for hosting us, as well as Red Hat and Mirantis for their support, and looking forward to their speakers next. Tonight I'm going to be talking about trusted computing and OpenStack, and talking a bit about what trusted computing is and why it's relevant and how it fits into the OpenStack architecture. So kind of as a leading question, we're used to cloud computing and bare metal clouds, and Rackspace recently launched its on metal. So this is a bare metal cloud offering, and the idea is that you can get a single tenant bare metal machine by the minute, and that you can use this exclusively. So in some ways this is a much better security story than kind of the Amazon world, where they actually control the hypervisor and you're running a virtual machine. In this case, you control the entire stack and are running on this bare metal machine. But how safe is it really to run on a machine that somebody else may have had bare metal access on before? Rackspace probably has good security practices and is sanitizing these machines between users, but you can imagine that on other providers, you may not know what you're getting on this machine. Now, what can somebody actually do with a server that they might get from a bare metal provider? Well, in the news lately, there have been a lot of developments around attacks that aren't necessarily at the operating system or hypervisor level, but are beneath it in the platform itself. So recently we had a lot of revelations about the NSA and numerous programs they had that were attacking the BIOS of a system and other parts of firmware on the system. So things like the master boot record, different device controllers and firmware. There have also been some BIOS viruses in the wild. One that's a couple years old now is called Mebroni, and this has been an increasing threat. There's people having malware that's targeting not just the operating system, but being persistent in the platform itself. So targeting BIOS, different parts of the firmware, different parts of components that load up in the boot process. Now, what's actually vulnerable? Well, it turns out pretty much everything that boots up or is touched in the boot process has been attacked with some vulnerability. So this is EFI, it's the BIOS, all sorts of firmware and op-ROMs that are loaded as the system boots up, disk firmware, even keyboard controllers themselves. Pretty much every single piece of firmware on a typical server that you boot has at some point had some vulnerability demonstrated. Now, not all these have been in the wild. A lot of them are typically something you'd find in a black hat talk, like a proof of concept, but the threats are out there. And as some of these NSA revelations showed us, they're actually being exploited by at least a state actor. If they're able to do it, and this is common knowledge from the security community, there's no reason that other attackers can't be using these techniques. So if I wanted to, I could get a bunch of bare metal servers, try to embed some persistent firmware, and then their next users might be vulnerable to me. So the question is, what can we really do about it? And are there really implications about this? So one standard that's come up is from NIST. And this is NIST 853. And they've got some requirements in this set of standards for actually returning a system to a known state. So the idea is that if you have a bare metal server and give it to somebody else to run, how do you actually know how to get the system back to a known state? If I give you my computer for an hour and you can do anything you want with it, and I get it back, how do I know what you did to it? So there's some technology and some tools out there that we can actually address this. And one of them is trusted execution technology. So in this diagram, this might have a pointer. No. In this diagram, I've got a picture of a CPU and all the bits of firmware and software that are loaded into the CPU at some point in time during the boot process. And as I mentioned, every single thing in this diagram, which isn't exhaustive, is vulnerable or has been demonstrated to be vulnerable at some point. Not necessarily all current, but at some point people have demonstrated vulnerabilities in this. So the way that trusted execution technology works is that it uses a separate component called the TPM, Trusted Platform Module. Many of you may be familiar with it. But if you're not, what it is, it's a small, secure coprocessor that's outside of the CPU. So it plugs into a motherboard or is soldered into a motherboard. And what this TPM can do are crypto operations. It's got some private key material in it and some internal storage. as well as something called a platform configuration register. And these are special purpose areas that you can store measurements. So what the TPM does is actually take all these measurements of all these components that are required to boot up a system. So it's the kernel, the BIOS, different command line parameters. They can all be measured through the CPU and stored in these special registers in the TPM. And then later on, when somebody uses the system, they can connect to it and engage with a protocol directly with the TPM and do something called remote attestation. And what this does is that me as an outside server can connect to the system, and I can communicate directly to the TPM and get a signed statement of all these measurements. So it kind of acts like an auditor and signs off and says, here's what booted on the system, and I'm a valid TPM, and you can verify that. These TPMs, as I said, had some key material baked in. I can verify that key material all the way up to the manufacturer. So it's got a certificate chain similar to what you'd find on a website. So once I do this, I basically have a statement that is an attestation that this particular system booted up with a particular set of firmware and software. So this is a very powerful construct. So I can take that system that somebody else leased for an hour, I can get it back, and I can boot my own software on it. And just as a check to verify that it actually booted with what I expect, they didn't change the BIOS, they didn't compromise the op-ROMs or any other piece of firmware, I can use the TPM as a trusted piece of hardware. So what do we actually get out of these measurements? And just as an example, I've got kind of a snapshot here of some measurements. And it's a little hard to see, but what these columns are is these are hash values that are stored in these configuration registers. And on the right, I kind of classified them with these color labels, the different things that are measured. So it might be credentials, the operating system, the BIOS, authenticated code modules, command line, boot parameters, pretty much everything that went into loading the system, I can measure and get a report from. And so this is just a sample of what you might see from a TPM in this remote attestation. So it's not a foolproof security system, so I just want to go through some of the gaps in it today. A few things about it are that you can measure a lot of this firmware. So I've got this kind of labeled as the provenance of the BIOS. Well, today we don't really have a great authoritative list of what's a good BIOS and what's a bad BIOS. So if I measure it and I don't know what it's supposed to be, it's not very useful. Some of the other attacks are kind of historical. So one funny was in the first version of the TPM, you could actually compromise this with a paperclip. So there's a set of connections between the TPM and the CPU called a LPC bus. I could touch one of those with a paperclip and actually reset this TPM into a state that I want it to be in. Some other things I mentioned are that you can actually spoof this bus between the CPU and the TPM. So like I said, it's not foolproof. If somebody's in your data center, they can interpose that. And also, it's possible to extract keys from the TPM. It's not actually designed to be resistant to physical attacks. So, not foolproof, but definitely a step above the status quo, which is just trusting whatever's there. So where does this all fit into OpenStack? So we've got this kind of tool that we can take a system and boot it up and get it into a trusted and known state. Kind of what the NIST 800-53 was asking for. He's getting a system back into a known state. Well, OpenStack has this concept of trusted compute pools, and it's pretty straightforward. So in this picture, I've got a user, a scheduler, an attestation server, and then a couple compute nodes. And right now, these compute nodes are potentially untrusted. So if this user wants to run some payload on a node, you can ask the scheduler to run this payload. And the scheduler can ask this attestation server which nodes are actually trusted according to some policy. Now again, this could be compressed into one component, but essentially treat the attestation server like an independent service. So what the server will do is contact each one of these compute nodes and perform that remote attestation. So it'll say, give me a signed statement of what you actually booted up with. So when it does this, it can actually establish which ones are trusted according to some policy. So in this case, maybe the second node is running a BIOS that's not recognized, or it booted an old kernel that is known to be vulnerable. Whatever your policy is, this server can read those values and decide, all right, this booted up with what we expected to be booted up with. And then it can return that report back up to the scheduler. And at that point, the scheduler can decide to run a payload on this trusted node. So this is kind of the state of the world today. This is essentially how this trusted compute pools work, and this notion of having a trusted filter that will filter out the compute nodes and give you the ones that you actually trust with your payload. Now there's some gaps in this model. Do you have a question?
Can you please explain the third step, like how it's going to check the attestation?
Oh, right here. Okay. So this attestation server I've kind of got as an abstract construct. We haven't really talked what it does. But what it can do is, whatever your organization has may have a policy that says, we trust these BIOSes and these operating systems and these particular configurations. So what this attestation server will do is contact a compute node and ask the TPM and say, what did you actually boot up with? And that TPM, independent of what's booted up there, can respond with a signed statement saying, compute node A booted up with this version of the Linux kernel and this version of the BIOS and this SN and everything else that came up with it.
Do you have to load the hashtags into the attestation first?
The attestation server, it doesn't necessarily need to know them a priori. It can actually compute them from just the input values, so like the kernel and other components. It's kind of done different ways. So some implementations may have a white list of just the hash values. Some other implementations actually can generate it from the known kernels and known BIOSes. Yeah, it's a good question though. Okay, so it's a good question of like, where do you actually get this policy? And there's not an authoritative answer. So like I said, things like the BIOS, there's not a list from Dell and a list from HP saying these are all the good BIOSes and the measurements you expect. So there are gaps in this that an organization using this would need to figure out what to do. So as I mentioned, there's a few implementations out there, and probably the most well-known is Open Attestation, or OAT. This is an open source project. It's originated largely from Intel. There's also some code from the NSA in there. Mm-hmm. No joke, NSA's got some code, and they've got an interest in trusted computing. So fortunately, it's open source, so you can look for their backdoors in it, but it's up there. Intel's also got a enterprise version of this open source project internally in some documents. It's called Mount Wilson. They've now called it the Intel Trust Attestation Solution. Kind of rolls off the tongue. But that's an enterprise version of this that I think basically Intel customers can get access to. And then our company PrivateCore also has a implementation of an attestation server. This one's built on some different technology, kind of more modern Python Django, and uses the Horizon UI elements. So several different implementations out there, and they're available both open source and as proprietary solutions. So what are some gaps in this model? Well, you recall from that diagram, we've got this pool of compute nodes, and one question is, where does that scheduler actually run? In most cases, people are running kind of their OpenStack components alongside their compute nodes. And in that current model, it's kind of assuming that you've got these services in some already trusted environment. It's only attesting the compute nodes. So it's a question of how do you trust whatever Nova's running on or anything else might be running on. A second issue is, let's say you've got these compute pools and one of them is bad. Well, that compute node is in your OpenStack system, and it's got access potentially to some of the images and other systems on there. So you're kind of assuming that there's some other access control between potentially bad nodes and this control plane. So it's a little bit of a weird model that you might have a filter that looks at a list of servers and says, oh, this one's trusted, I'll run a payload on that. And then somebody comes in and doesn't use the trusted filter and you run it on one of these other nodes. It kind of doesn't make sense that once you know that there's some bad nodes in there that you would continue using them. So as a potentially better model, this notion is that you could reduce a trust perimeter to just your kind of key credential storage and your attestation server, while your OpenStack components and compute nodes can be out there in some potentially untrusted environment. So whereas today we just attest the compute nodes in a trusted filter, we would also want to attest those OpenStack components. So before you boot up your scheduler, before you boot up anything else, you attest the actual platform, and then you can bring it up. So this kind of fits into some of the OpenStack projects like Iconic, that are about bringing up an OpenStack system. So in that boot process, you'll want to make sure that the server is trusted. At this point, we'd also attest these potential compute nodes, but don't actually give them any access to those components yet. The next step would be that we would take the results of this attestation and give it to some policy engine that can decide who gets what credentials. And then this credential storage can actually provision those compute nodes with some key material. And at that point, those compute nodes can join whatever control plane that the rest of the OpenStack components are on. And the idea here is that they won't a priori be in that pool of servers. They won't get to actually join until they've been attested. So I do know that some people's deployments will kind of do this ad hoc where they will have some network-based admission or other sort of kind of access control. But having this tied to attestation, so you never give any credentials until it's been tested, is one way to ensure that you don't get any of these untrusted nodes into your pool. So kind of summarize some of the improvements and some of the things that would be good to happen in kind of the general security landscape. So first off is actually attesting all components in an OpenStack deployment and not just compute nodes. So if you bring up a scheduler or some other service on an untrusted node with a compromised BIOS, then your whole system might be compromised. So really you need to attest everything from the start. One thing that would be a positive development is for cloud providers to actually provide TPMs. So Rackspace is one of the ones that does have TPMs on their servers. And you can make use of them as a user and actually use some of these trusted computing tools. Other providers don't necessarily have it, or they don't have the BIOS updated to take advantage of it. So I think it'd be good for cloud providers to kind of standardize around this and make these TPM-enabled systems available to their customers. One thing missing from the vendors, so people like Dell, HP, Supermicro, is providing an authoritative list of what the expected firmware is. It's surprising that with this trusted computing being available for several years now, that we still don't really know which BIOSes are good. The best we can do now is look what's out there on our systems, figure out and decide that those are expected, and then look for changes later on. So it's very hard to distinguish a good BIOS and a bad one today. Do you have a question?
Yeah, so what happens when you upgrade the BIOS?
Yeah, it's another good question. What happens when you upgrade the BIOS? So let's say I do upgrade my BIOS. How do I know that that upgrade is good? Hopefully it's signed by the vendor. And then also, how do I update my whitelist policy? So I need to have some mechanism to take those known values and say, all right, version 1's already in there, version 2, I'm going to update it, and then at some other later point, I want to actually retire that first version. So you kind of need to have this whole process of keeping this whitelist of firmware updated and being able to know which ones are good. But like I said, today there's no authoritative resource where you can look and say, yeah, this is a real update, this is the real value I expect, and if it's different, I should worry about it. You kind of just need to update and see what the value is and hope that that's good.
Can you generate a hashtags or whatever list with the existing system and keep it like a standard?
Yeah, so you could take existing systems and start building up a database of values. And
trusting other vendors, like say I have one gold system, I take hash values of it and keep it in my attestation server and try to compare everything whenever a system comes into compare with these values. Yeah,
so that is one approach, and trying to build up a database of known BIOSes. And the problem is how do you know that's a gold system? I guess you can tell that it looks like other systems and you picked it from a pool of them, and they might all be compromised, or you might have lucked out and gotten the right BIOS. So there's not really an answer. There's not a way to know for certain that you've got the right BIOS. But as I said, if you get a bunch of systems and they all have the same one and they came from the vendor, either they're all bad or they're all good. So the last one, this is more of a long-term ask of CPU vendors, is to reduce or eliminate the dependency on the TPM. So in that slide, kind of showed a lot of vulnerabilities in TPM, and the fact that they weren't ever really designed for somebody with physical access. Today, if somebody's running in a remote cloud, they could compromise this trusted computing by putting an interposer on that LPC bus or doing some of the other attacks. They're not necessarily cheap or easy, but they are known attacks. So in the future, it'd be great to have that TPM on a single package, or a newer technology like SGX out of Intel that might make it obsolete and be able to attest systems in new ways. Yes?
How do you actually secure the software that's doing the validation on the machine itself? Because if I'm a bad guy, I get in there, right? The first thing that I'm going to do is I'm going to overwrite that software. I'm going to take hashes of what the operating system should look like, what the BIOS should look like, and I'm going to send those back to the attestation server.
This is a great question. So he's asking, let's say I've got a compromised system and it boots up with the malware, and at that point I try to remotely attest it. So the trust execution during boot time is going to measure everything that loads to that point. So the idea there is it should catch that malware in the measurement. So the TPM will get a measurement of the malware, and by design, once that malware boots, it would be a flaw if it could just wipe out those measurements and put its own values there. But the way these special registers work is they can only be updated in certain states during the boot process. So there's a special instruction called senter that allows you to zero out these registers, and then you can only update them with a hash chain. So you put the first value and the next value is a hash of that and a hash of that. So if the malware boots up, it can't just say wipe out the old bad BIOS and put in a good one.
I guess what I'm saying is actually overwrite the process that sends the value to the attestation server, so that instead of sending this thing that says it's bad numbers, have it send good numbers. Yeah.
Another good question is I connect to the system and I say, give me the report from the TPM. Well, this is by design a challenge response protocol with the TPM itself. So the idea is that TPM's got a public key and it can sign values. And so when I connect to this potentially untrusted system and I say, all right, system call, give me the quote from the TPM, I'm going to provide a challenge to it. So that can't be answered by the malware. It can only be answered by the TPM. And you can't man in the middle of that protocol. So I send a challenge, and then I'll basically look for a signature of the state of the server and my challenge from the TPM. And if that malware that's sitting in between tries to modify it, it'll invalidate the signature. So you kind of think of the malware just as like somebody on a network connection. Like they can spoof things, they can jump in there and change bits, but as long as the two endpoints are authenticated, then they're not going to be able to manipulate that. So yeah, it kind of reduces that server to like a network connection.
You still need an out-of-band key for the TPM.
Good question. So it was, you need a out-of-band key for the TPM, and that's correct. So you need to know the public key of the TPM. Now, they typically come with a public key certificate that's signed all the way up to the manufacturer. So you can take an unknown TPM, connect to it, get its public key, and then validate that up to
but how do you get the public key from the TPM if the TPM is at Rackspace?
The TPM's at Rackspace. So you can do a challenge response protocol again with the TPM. So you connect to something. You don't know if it's real. It might be a simulator. And you say, thing that I think is a TPM, answer this challenge.
No, but the key. You still need to get the key first somewhere.
It's a public key. So I can say, give me your public key and prove to me that you have the private key.
Oh, I see.
And so I do this challenge response protocol, and then this is called a...
Yeah, but in that case, you actually do need the public key out of band, otherwise the malware can just have two pairs.
No, you have the trust chain.
There's two ways. So some of them have a trust chain, and you can rely on that. Some of them don't ship with a trust chain. So in that case, you're kind of out of luck, and you need to trust that you got the right public key. So some of the TPMs don't actually implement it properly. So it's definitely a case that comes up with where you might get a remote server and it has a TPM that doesn't have a valid chain, and you don't really know whether it's a real TPM. It might be a simulator.
And how do you invalidate chains? Because the TPM, the key is baked into the chain.
Key's baked in, so if that intermediate certificate gets compromised, you can't invalidate it. So it's baked in there, and there's not a way to change it. So it's a very good point. Yeah?
So you mentioned some of the limitations, vulnerabilities. So you mentioned the, is it pin count plus?
Yeah, LPC.
But you need physical access to the server, you need to get access to the data center, you need to open up the CPU, you need to, you need what, so outside of that physical kind of vulnerability, what other limitations?
So the protocol is designed for somebody without physical access. So if you trust that Intel and the protocol is correct, then there's not really known attacks against the trust execution. But once somebody has physical access, then all bets are off. And we're really talking about somebody running this in a remote data center. So, you know, if I'm running it,
The risk is low, right, today, or not?
why is it low?
Because you're saying that you don't trust your data center users, folks getting physical access.
Yeah, why would I trust a data center? Like, I don't know who they let in there. I mean, I want to run on a system and not have to trust their data center, right? Like, why would I trust guys who are in there, you know?
have to have physical access
Yeah.
to do the hack. Right?
Yeah, you have to physical access to put something in LPC bus, yeah. But yeah, there's no reason to trust that data center security is going to protect your server. I mean, they can have best efforts and try to protect it, but at the end of the day, I would like to be able to run and not have to rely on, you know, whoever happens to be operating that data center. Because it's very, you know, there's been a lot of like penetration testers who can show that it's like very easy to get in these data centers. I know some guys who run at a big consumer service down the block, and they have stories where they climbed over the top or where they, you know, powered off systems with sticks and things like that. So don't count on them to protect your server.
Very trustworthy data center, isn't it?
Yeah, well, it's a few blocks away, so.
Okay.
Yeah.
In the picture you showed, kind of like the option ROM, like yeah, it's way back. It shows the option ROM going down to the CPU.
Yeah.
Yeah. So is it guaranteed the CPU has access to the entire BIOS on, say, the network interface card to guarantee that it has a hash over the whole thing and that it hasn't been changed?
Yeah. So this.
This was a discussion that came up a lot in the Ironic offers the bare metal as a service for OpenStack, and the risk was always somebody will flash the network interface card firmware, and there won't be a way for anything outside of the network interface card to tell the difference.
Yeah, so there's two different types of measurements. There's a static root of trust measurement and the dynamic root of trust. And I guess in this picture, the static root are all the darker blue. So that would be the OptROMs and like the network card firmware. Those do get measured. Historically, the static ones have been really problematic because if you change your network card, all your measurements change. So you need to know how to reconstruct those a priori based on, you know, the other measurements. Otherwise, you know, if you get updates to firmware or BIOS, it can invalidate those. So I think to answer your question is yes, it's supposed to be able to read all these different OptROMs before handing off to the next part of the boot process. Yes?
How does it deal with hot swap things?
So like hot swap devices, that's a good question, and I actually don't know how it would account for like hot swap network devices. My guess is that it would not be handled because it's at boot time for a static root of trust for OptROMs, and yeah, I don't think that would actually be covered. So that's probably a vulnerability in this if somebody hot swaps. All right, well, that's pretty much all I had. So thank you very much, and we'll be around after you have any questions.